Yeah, it's in. Yeah, is there power? That would do it. All right. Aha! There we go.
Ladies and gentlemen.
All right. So thanks, everybody, for coming out. So my talk today is Async Everything. Just real quick, during the day, I'm a mild-mannered programmer who works at Living Social, writing big code. At night, I fight the scourge of bad domain and DNS providers out there under DN Simple. So that's what I do. But I'm also a customer. I use a lot of software, obviously. I think we all do. We're all customers. And I build a lot of web software. So the web area is where my main focus is most of my day. And as a customer, one thing that's really important to me is that stuff works fairly fast. I don't want to spend a lot of time waiting for a web page. And the amount of time that I'm willing to wait has been going down to less and less every day. So if it's taking more than a couple seconds, I get frustrated now. It used to be that the goal was 8-second response times. I can't even remember a site that I could use that had 8-second response times these days. It's just non-existent. So latency costs money. In 2006, I believe it was, Amazon stated that for every 100 milliseconds of latency, they lost 1% of their revenue. All right? So if you're doing 100 million in revenue a year, that's a lot of money to lose for 100 milliseconds. There's also, Google also came out and said that a 20% increase, or an increase in latency of I don't know, it was like a second or a half a second or something, like reduced traffic or reduced responses by 20%, people clicking on ads and things like that. So clearly there's actually a financial cost with latency. So what are some of the causes of latency? Well, there's actually a study that basically they looked at for web applications, what was the major cost of latency? And it comes down to the amount of time for the infrastructure, so that's actually the hardware response time. It's the amount of time that it takes to run the process on the server. So this is the time where it's sitting inside your application doing stuff. The amount of time that it takes to go over the network, so this is the transmit time. And then the amount of time spent on the client side actually rendering the thing. All right? And in that study, they said that only a tiny portion of the delay is actually on the server. Except when it isn't. That's what I added. Because in fact, when you're building applications these days, I don't know about your guys' applications, but I spend a lot of time integrating with other services. Like a lot of what I do is calling out to other web services to have them do something, whether it be billing or maybe a service that I depend on that's not core to my business, but that I can use to make a little bit more money, whatever it might be, or to have a better customer experience. And so it's actually compounded because it's not just my latency I'm dealing with, but it's actually the latency of the services I have to connect to as well. All right, so there's no doubt that a lot of time is spent just delivering over the network. And when I say a lot, it's all relative. When you're talking hundreds of milliseconds, that's a long time if you're having your packets are traversing, for example, the Atlantic for services that are here in the US that are being serviced in Europe or even further about. So what are some of the ways of dealing with this latency? Well, first of all, I'm going to give you a few steps that you can use to generically deal with, well, any sort of problem that's a performance issue. So dealing with a latency problem, the first thing that you have to do is measure. All right, this is the key thing. If you go ahead and think that you're going to solve the problem without measuring where the latency actually exists first, then you're probably going to end up with a solution that doesn't really solve the latency problem. All right, so the first thing to do is measure the latency, and there's plenty of tools out there. I mean, you guys all know the tools in Ruby land. You've got things like New Relic. You have external tools that can basically ping your system from all over the world to determine what the response times are. So there's plenty of tools out there. The tools are not important, but the measuring, the act of measuring is extremely important. The second step is you actually have to think about it. Okay, so you've measured and you see that there's oh crap, there's latency here. Oh, quick, let's go fix it this way. No, the first thing is to just slow down, take a breath, and go, I wonder what's actually happening here. Let's try to reason about it. So after you've spent some time reasoning about it, then you can actually build a solution or purchase a solution or change something to solve the problem. And after that, you verify it with more measuring, all right? And you do it again and again and again. Because chances are once you solve one latency issue, well, then you're going to have another one and another one. They're going to get, hopefully, if you're doing things well, they're going to actually be small. The latency times are going to come down. But just don't forget that as you build more stuff on, guess what? You're probably going to add other latency points back in as well. So it's important to think of those 4 steps there and to actually do them. All right. So now it's story time here. I'm going to give you guys a few little stories and some examples in my career where it was important to actually use things like asynchronous processing and asynchronous I/O to solve issues with latency. All right. So story number 1. This is for DN Simple, so this is a relatively recent problem. Part of what we have to do is we don't handle our own internal billing system because writing a billing system is not hard, but it's time-consuming to deal with all the stuff that you have to deal with dunning and making sure that your customers are paying their bills and notifying them via email, sending receipts, so on and so forth. So hooking up to an external service provider, what we found is that there are variable response times. So most of the time, our customers would experience a nice little, maybe it was 100 milliseconds to go out to the service, and then our server answered, and so maybe it was a second, all right? And they're fine with that, okay? But other times, seemingly randomly, it would just sit there and hang for 10 seconds, 15 seconds, to the point where sometimes it was actually timing out Nginx's maximum response time. So say, okay, I'll cut 30 seconds, we're cutting off. 30 seconds, I mean, that's insane. So we have this variable response time that's completely random. All right, this is a problem. So what is one of the solutions that we could have picked at? Well, the solution we chose here was asynchronous processing. Okay, and so what this is basically saying, I've got some work that needs to be done, and it depends on something else, so I'm going to actually do that elsewhere, and I'm going to respond back to the customer very quickly. All right, and in that case, we used Resque. All right, so we basically had said, okay, we're going to have a Resque job that's going to go out and it's actually going to do the process of calling out to the gateway and saying, okay, make a charge against this card, come back and give us a response, and so on and so forth. And what we presented to the customer was a holding page that essentially would refresh. I mean, it's a simple, stupid solution, right? But it worked. Because the bottom line is the people, when it responded really quickly, they would hit that holding page, and then it would just refresh really quickly and actually go into their domains, and they're set up. It's paid. For people that take a little longer, it might sit there, but we gave them an exit. We said, you can continue using the app. You don't have to wait for this, but your account won't be activated yet until this processing is done. And it works quite well. And yeah, we took a really simple way of approaching it through, honestly, a meta refresh, but it worked. All right, you could do it through Ajax or whatever, it doesn't matter. But the point is to let the customer continue on without delaying them, because quite frankly, they don't care if your credit card processing takes a little bit longer. They just care about continuing to do their work. All right. So that was the first story. Second story was back when I was working for Chimp. I don't know if you guys know Chimp, chi.mp, but it was a service that I worked on a couple years back. And one of the things that it did is it aggregated all of your stuff. All right, supposedly into a domain that you own. And it aggregated all the stuff from like RSS feeds and Twitter and Flickr and blah, blah, back when social aggregation was hot, back in 2005 or 6 or whatever it was. And so the problem that we came at is we actually experienced a decent amount of growth. And while we were trying to retrieve RSS over HTTP, we had processes that were already asynchronous processes, because they would sit out there and they would run externally and they'd update the database. But the problem was that the lag between when that process would start and complete was getting longer and longer and longer. And sometimes it would just hang. It would never complete. We'd have to kill it. So in this particular case, asynchronous I/O to the rescue. All right, so asynchronous I/O uses part of the OS underneath to basically say, okay, I don't want to sit there and block waiting for I/O to come from wherever the I/O is going to come from. I'm going to return back to the processing, and you're going to register some sort of a callback. And when we actually get data, we'll go ahead and invoke that callback. So that's how asynchronous I/O essentially works. Pretty straightforward concept. So we did that, and we were able to get some really good improvements. But the problem is that parsing and processing still takes time. So ultimately, we tried to use threads. And if you've ever done async I/O and threads, it's hard. I mean, it's just really hard to get it right, because you can get weird deadlocks. And if you're in Ruby land, trying to actually discover those deadlocks is pretty insane. We were on JRuby at the time doing this particular processing, so we were actually down inside of like a Java profiler trying to figure out what the hell was going on. And the truth of the matter is we just got lazy and said, let somebody else handle it. Because ultimately, that actually worked really well. We had an external service that handled it. They called back. They became our asynchronous I/O and processing service. Sometimes that's the right solution. Sometimes you got to be lazy. All right, so final story here. Final story, and then I'm actually going to probably show you guys some code just so we can see some examples, just so I'm not just telling stories. So this actually isn't about code. This is about people. All right? Remember the talk was async everything. I'm not telling you just to asynchronize your code, and that makes sense someplace. I'm telling you that sometimes, if you do it well, you can actually have asynchronous processes with humans, and it works super. So that's me. And that's my brother. My brother and I work together on DN Simple. And we're 9 time zones apart. So there's not a lot of overlap. All right? So synchronous communication is great. It's simple. It's really simple. You call somebody up and you talk about something, you find a solution. Except when you're 9 time zones away. Or 12 in the case where I was actually working with people in Hawaii as well. So sometimes what we found was that coming up with a good, repeatable asynchronous solution for human-to-human communication actually made things a lot easier to deal with. It's scalable. And the reason it's scalable is because we can actually drop a lot of messages to each other and deal with them as we have time to deal with them. And we can prioritize our work. So for example, if a customer support issue comes in, that's pretty critical. But if I'm sitting there and I'm on a conversation with my brother and we're trying to solve something, now I've got to choose between which of these things I'm going to deal with. Am I going to deal with the customer service issue, or am I going to deal with the thing I'm working on with my brother? One of them's going to suffer. But if we're working in asynchronous mode, then he just sends me, we have a discussion, it could be via email, it could be via Campfire, it doesn't matter. We have a little discussion, and we deal with it in an asynchronous fashion, and I can go straight to handling the customer support issue. And remember what I said in the beginning. All of this stuff that I'm talking about, making things asynchronous, really has one goal in mind, and that's to improve the happiness of your customers, all right, whoever that may be. So I think the neat thing is when you're building out these asynchronous systems for businesses, and I'm a big fan of this. I'm a remote worker, so I really like the idea of building companies around asynchronous processes. There's still a whole bunch of people out there that debate whether this will work. I think it's a grand experiment. It's a lot of fun, and I think it's important, if it does work, that we share about how to make it work. So that's part of, I think that companies built around asynchronous processes instead of synchronous processes like meetings and phone calls are going to have a better chance for success in a world that moves really fast. And so I'm a big proponent of that. So my message to you there is embrace asynchronous communication now. Start using it and try to make it work for you, even if you're sitting in the same office as the other developers or the other people in your company. So none of this is really mind-blowing, all right? This is like, great, okay, I've told you something that's pretty simple. What they really are is anything asynchronous, it's a tool. It's a tool like anything else, and you have to know when to use it, and you have to get comfortable enough so that you can wield that tool like a professional. So let's take a look at some of the tools that you might be able to use. All right, so I've got a few examples here. How's that? Everybody can see that? Okay, excellent. So what we're looking at here is a little EventMachine code. So if you've never heard about EventMachine is a asynchronous I/O library that is done in Ruby. So it's interfaced on Ruby on top of asynchronous I/O from the OS. It works fairly well. You can use it to write servers. There's a number of web servers like Thin that were written originally using it. And there is, I don't know if Goliath uses it under the hood. I think it does. But anyway, the point is that there's plenty of tutorials out there for how to use it. I'm just going to give you a quick example so you can see how it works and how it runs. All right. So essentially what I'm doing here is I'm kind of resolving that problem that I was talking about, but a really basic. What I'm doing is I want to download a bunch of web pages. All right. So I want to download them, but if I sit there and wait for the ones that are really slow, then it's going to take a long time to do everything in a synchronous fashion. All right. I could try to do it via threads. That would work as well. But for this example, I want to use EventMachine. So I load up the URLs from a file, and then I go into the EventMachine loop. And the EventMachine loop is basically sitting there and waiting for I/O behind the scenes so that your processes don't have to. I queue up HTTP request for each of the URLs. This is built into EventMachine. They've got a little library. It's not built in EventMachine. It's a little library called emHTTP. And then I register a callback for when it succeeds. So this is just a block. And then an error callback for if it fails. And inside of that, I'm just going to print the response. I bet I have a laser on here. Is the red the laser? Oh, yeah, I got laser. All right, so we got the callback, we got the error back. All right, really simple. It keeps track of how many URLs are still pending so that it knows whether or not it needs to stop in either case. If it doesn't need to stop, then as soon as it exits the callback, then you're basically back waiting for the next callback. So let's see this thing run real quick. So I got a few demos here. So that's the code to run it. All right, it's getting that's it, it's grabbing it. So grab those in parallel. Now the interesting thing to note here is if I look at that urls.txt, that's not the order that I registered them in. They came back as the data was coming through, all right? And so the longest that we really have to wait is whatever the longest response time is. And in this particular case, it was for the rubygems.org site, all right? And all I did is I downloaded them into the files directory here. And you can see if I open one of them, I'm going to get everything, all the HTML, without any of the images or anything like that. So really simple thing, but the thing is that I didn't have to sit there and write a process that looped through each one of these in block. All right, so that's the goal of things like EventMachine. That's one example. Next example. So there's another library out there that's kind of interesting. It's been mentioned a couple times here. Brian mentioned in his talk. It's called Celluloid. So Celluloid is essentially a Ruby implementation of some of the ideas in Erlang, an actor implementation, if you will. So let me just real quick show you the code here for this. Now that's actually the Erlang code. We'll go to that in just a little bit. So here's an example actor. It's not really doing much. It's just sitting there and it's saying, OK, I'm going to start up the actor. I want to say whatever this line is 10 times, all right? And then the main thread's going to go to sleep, and then inside this, I'm going to sleep for a few seconds, and then I'm going to run this, okay? It's just a toy example. But what we can see is when we actually run it, I'm going to actually slide this over here. So notice what it did there in the beginning. It went into the actor, and it says, I'm executing, I have 10 lines to print, okay? And then the main thread went to sleep. So, and then it came, and the main thread's sitting there sleeping, and the actor then 5 seconds later comes up and does its work. So you can actually accomplish the exact same simple thing in threads, because basically what Celluloid does is provide a nice abstraction on top of threads, a simpler API to use, and it actually adds a lot more with things like supervisors. So if you have a lot of different actors that are out there doing things and actors die, you need something to actually capture that and then restart those actors. So Celluloid provides that, and it really does, it basically provides what Erlang has as built-in part of the language. But I could do the same thing with threads here too. So you see this little example right here. I'll just run that. Let me get out of this because it'll just sit there listening forever. Same thing, right? Exact same behavior because that's what Celluloid does under the hood. So that's Celluloid. Celluloid also is kind of interesting because Tony Aseri, the one who's working on it, is trying to do a bunch of different things with it. So for example, he also has Celluloid I/O, which is like a non-blocking I/O plus process plus threading. So that's actually even more interesting because that's hard. Remember I said that earlier back when I was doing this in JRuby. It's just hard to do well. It's really hard to reason about. It's hard to not have it blow up and have deadlocks. So while his library can't stop you from writing code that creates deadlocks, it does help reduce the likelihood of it. So another example here. So this should be, I think, the final example. No, actually, I'm going to give you one more after this. So 0MQ. 0MQ is actually a C, bit of C code. 0MQ is what's called a brokerless messaging queue. All right, so the way messaging queues typically have worked in the past is there is a broker or a set of brokers that are servers that run, kind of like a web server, but in this case, all they're going to do is they're going to handle messages and deliver them off to different queues, right? They're going to either deliver them, like there's going to be a one-to-one, I'm going to sit there and I'm going to publish to a queue, and then I'm going to listen to it. Or alternatively, they might say, I'm going to publish to one, and a whole bunch of different systems can listen to it and act independently. All right, so message queues are actually a really important part of building a distributed system that can continue to grow and scale over time. What's interesting is 0MQ takes the approach of a brokerless message queue. So they say it's just like using TCP, only it's queue-based. All right, so that's kind of interesting. What I'm going to show you real quick, I'll give you the code first so you can see this. So this is going to be a simple pub/sub implementation. All right, so what we have here is we have a little 0MQ context. There's libraries for 0MQ in pretty much like all the major languages. So that's one of the things that's interesting about queue systems is that you can interop between languages very easily. Kind of like how HTTP is really beautiful in that fashion. It's just HTTP is better for synchronous communication. So we're going to get our channels. We're going to open a socket, which is a subscription type. We're going to connect to that. And then we're going to say, hey, this is I want to subscribe to that channel. And then if we control C out, we're going to trap that. And we're going to close out the subscription. Otherwise, we're going to receive and we're going to print a message. And then the other side is the publisher. And the publisher is essentially getting off the side of the screen. That's what it's doing. Let's move that over here just a tab. So the publisher is just going to say, OK, I'm just pumping stuff into this socket. So I'm going to bind to that particular port on whatever host, on the local host plus other whatever. It'll go to all your hosts, I believe, on the local. And then I'm going to send a message to that channel. All right? So fairly straightforward. In order to see it work, what we're going to do is we're going to start a subscriber on channel 1, a subscriber on channel 2, and a subscriber that listens to both. And then over here on the publisher, we're going to start that up. And what I have to do is I have to tell it what channel I want to send to. OK. So you see what just happened there. These are different processes, but this one received it, this one did not, and this one received it. If I send to channel 2, you'll see that this one down here got it, and this one got it as well. So 0MQ is a very simple way of building a brokerless queuing system where you don't have to actually stand up the broker and actually host it, which has really, it's neat. I mean, it's a neat concept. So it's worth looking into to build distributed systems where you don't want to have a broker in the middle. All right, so one final example, and then you all can go to lunch because I know you're getting hungry here. All right, this final example, a little bit of Erlang. Couldn't walk away without getting you a little bit of Erlang. All right, so Erlang. If you've never seen Erlang, it's got this like funky syntax. It's functional language. It's like, woo, you know, it's like Greybeard style stuff, right? But not really. What it is it's essentially a really great language for building concurrent systems because it's all built into the language, right? It's either built in the language or the standard libraries, and it's really good at running a bunch of lightweight processes and then monitoring those processes so if they die off that you can handle the errors. The same type of thing that we saw in celluloid, but built into the language. It's got a whole bunch of other neat properties as well, like a really awesome pattern matching. So let's just real quick walk through. This code was inspired by Brian's talk. I was like, I wonder if you were doing a simulation, could each actor in Erlang actually be kind of like a person, right? And if you were doing that, what's the maximum number of actors you could have in Erlang before it blows up? All right, so I was thinking, this probably won't work, but it'll be fun. Erlang, by the way, has the same problem as Ruby. It's slow, for whatever that means. What it basically means is that if you're processing binary data, it's slow. All right, if you're doing concurrent messaging, it's fast as hell. All right, so I think that's really important. It's got a great messaging system built in. It's got a really good VM under the hood with a lot of years behind it. So back to this. So what I'm going to do, and this, by the way, doesn't actually, when I simulate something, I'm not actually doing any of the calculation side. I just want to see if I could stand up 1 million actors, what would happen, all right? And it turns out, by the way, that the maximum is like 137 million actors is what it supports right now. So I was like, yeah, I could model something with that. So anyway, so I take the population and then the number of iterations that I want to run. I create the actors for it. And what if you don't know, a functional language is like an object-oriented language without classes. It's just like if you just take the things. That's what I mean. No, I'm simplifying here. I'm kind of fucking with you a little. But so what it does is it creates the actors. This is that neat pattern matching. So if the arguments are 0 and the actors, then just return the actors. Otherwise, if it's n, so anything other than 0, then start a link to the actor. So this start a link is basically saying I want to connect these two processes, these internal processes. It's never going out to the OS to do this. This is all internal. And then I'm going to recursively call create reactors. I'm going to decrease the number by 1. By the way, all this, there's no state that actually gets modified. That's one of the things that I'm sorry, I'm becoming a convert into functional languages. This stuff's just badass. I mean, no state. Nothing that I have to worry about that all of a sudden there's going to be random state that's just going to get in my system. That's fantastic. So anyway, I've drank this Kool-Aid all down. So then I'm going to add my actor onto the head of this list. This is just a little notation that says I want to add this onto the list, kind of like the arrows. And then I'm going to recursively call that until finally once we get down n hits 0, then we're just going to return the actors. So I have my actors. I'm going to say this is the number of actors I have. I'm going to create a list that's just basically a sequence of numbers representing my iterations. And then I'm going to go to the next iteration. All right, in the next iteration, same thing, pattern matching again here. If you have an empty array, then all you want to do is say, I've completed all the iterations. And I'm going to say, OK, I have to return something. So that's what I'm going to return. This little underscore here, by the way, means just ignore that argument because it's really cool. Erlang, if you have a function that has some sort of an argument that you pass into it, and then you don't use that argument, the compiler warns you. It doesn't like that. And conversely, if you try to use something that wasn't declared, the compiler warns you about that too. It's really neat. It saves a lot of problems. So I'm going to do that. I'm going to actually execute the iteration here. Tell me I'm executing the iteration. And then the iteration on says use this actor, like send them a message. That's the message sending pattern. Remember I said it was built in the language? It's like send this actor this message, which is a tuple of myself, my identifier basically, and ping, which is just a symbol that I can use, essentially the equivalent of symbol. And then I'm going to recurse. Notice there's a lot of recursion calling itself. This stuff I haven't done any tail recursion optimization because it's just an example. And then the actor on here, very simple. Right now, this is the part that it says I want to spawn a link back, and it says connect. So basically, these connects the two. So the main one could kill off these actors if it decided to wanted to. And then I'm going to receive messages with my process ID and the message. I'm going to print something out just for craps and giggles. And I'm going to recursively call listen, where I'm going to sit there and receive again. Each one of these actors is its own process. So that's the code, basically. And I'm going to go over here. I've already compiled it. I have the Erlang VM running. It's got a REPL, so I could actually sit there, or REPL, whatever you want to say, basically a way that I can just talk to the running processes. I'm going to tell it I want a population of 100, and I want to iterate 10 times. That's it. It's done. It didn't do much, but look at everything's all out of order, which is fantastic. Let me slide that over. I want you to see that. Whenever stuff is completely out of order, you know you've done something right if you're building an asynchronous system. That's the way it should be, right? You're not supposed to depend on any of this ordering. So great, it did exactly what I said it should do. If you look back up here, it's like, yeah, it did it. All right, let's just real quick, I'm going to close this out. I'm going to take a population of, I don't think I started with the full queue there. Yeah, 100,000, 10 iterations. Oh, see, that's the thing where I hit the system limit. So watch this. So I think it was plus P, I don't know, let's say 1 million. That'll work. And then I need that last one there. Hopefully I got the right. Oh yeah, that did it. It's running. It'll just run for a little bit. So the point is it can go, that's with 1 million actors going through n number of iterations. And the most amount, it's basically spending all its time writing to I/O right there. And with that, I'm done. Thank you very much. Everybody enjoy your lunch. Have a good day.